Hi, and welcome to part 10 of the Sound Basics series. We're going to be talking about digital audio in this part. So let's start with a sampling theorem. A band-limited signal can be reconstructed exactly if it is sampled at a rate at least twice the maximum frequency component in it. So, it's kind of basic. With digital audio, we can't capture an analog signal, a continuous signal, but we can sample it, right? You can capture at a very quick rate. So basically, you're looking at a signal, and then you're trying to grab a sample every once in a while. So here you have kind of a low sampling rate, and then a higher sampling rate, and a higher sampling rate. And if you have this twice the maximum frequency component, then you can more or less construct a signal exactly according to the Shannon-Nyquist theorem, sampling theorem. Now, why twice the maximum frequency? So the highest frequency we can hear is 20,000 hertz, right? More or less. So you need to sample at 40,000 times a second, right? And why is that? Well, because audio signals are bipolar, right? They have a maximum compression and a maximum rarefaction. If you just sampled at the actual highest frequency, so 20,000, for example, you're only going to get either here or here, but you're not going to get both. So it's not going to oscillate. It'll just be a flat line, right? All right. So Nyquist frequency is, again, at least twice the highest frequency that you want to recreate. And typical sampling rates here are 44,100 and 96,000. 44,100 is what we have, CD quality sampling rate. Now, why is that? Well, the reason it's a little bit more than 40,000 is because according to the sampling theorem, it needs to be a band-limited signal, meaning we do a low-pass filter and we get rid of all the sort of any information above 20,000, right? But filters aren't like instantaneous, so there's a little bit of roll-off. There's a little bit of space you need. So it's just slightly higher there so that we can capture all of 20,000 hertz, all right? And one of the main reasons you're filtering there is because of this phenomenon known as aliasing, right? So aliasing happens in video as well. Often thought of as like the wagon wheel effect, or like airplane propellers look like they're standing still, right? Because what's happening is it's oscillating faster than we're sampling. So if we grab, so if this is our actual waveform, but we're not grabbing things fast enough, we grab a sample here, and then we grab a sample when it's at the top, and then here, like that, and then we create a totally different waveform, right, than the one that we're actually trying to sample. So that's aliasing right there. If the sampling rate is not quick enough, we're going to get artifacts. So if you hear aliasing, in fact, you have a bunch of extra sort of artifacts in there. All right, let's look at a little video here.
If I have a signal frequency of 10 hertz, so it's a 10 hertz sine wave, and I'm sampling at 11 hertz, so I'm below the Nyquist frequency, which is required in order to preserve the frequency content of my signal, you can definitely see this alias signal coming up now, where that is not apparent in your incoming signal. In order to actually preserve that frequency, you need to go up to the Nyquist frequency. So now I'm sampling at 20 hertz, and you can see that it actually preserves that 10 hertz sine wave. But if you're just slightly above the Nyquist frequency, you can see that the amplitude information is not really preserved. You're getting this sort of modulated signal. You really have to go much higher than the Nyquist frequency in order for it to preserve both the frequency and the amplitude accurately. So here, if I go up to, say, 100 samples per second, you can see that it represents the sine wave better than just at the Nyquist frequency.
So let's talk about bit depth. So bit depth has to do with the sort of maximum volume we can get, or maximum loudness we can get from, and it's this vertical axis. So if we have a 1-bit depth, that means we can only sample at one level, one volume level, or one amplitude level, right? If we have 2 bits, we can do it here or here, 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 but no more of that. 4-bit, now we have 4 steps here and 4 steps below, and then 16-bit, 16 and below, above and below. Now, there's this thing called quantization error, and the greater the bit depth, the lower the quantization error. So if you look at the signal here, every time we come across part of the actual signal, we have to make a choice based on the available bits that are available to us, right? We can either go here or here, but we can't actually go in between, right? So you get the signal that looks like the red one because you're not actually having, because you don't have enough bit depth, you don't have enough steps along the amplitude region to choose. Then you have to compromise. You either have to go up here or go down there or go up here, right? But not in between. And then this is the resultant error. That's called quantization error. So if we look at signal to noise ratios and bit depth, and remember these are sampling values. These are digital audio. So we have integer values. So at 16-bit, we have 65,000 integer values, right? Meaning, we have 65,000 levels to choose from. At 20-bit, it goes up to 1 million, and then 24-bit, we got 16 million, 32-bit, 4 billion, 48-bit, 280 trillion, and then 64-bit, 18 quintillion integer values. So remember, bit depth is important because our ears are quite sensitive to changes in volume, right, in loudness. So there's a huge dynamic range that we're sensitive to. So the higher the bit depth, the more we can replicate that volume range, right? Typical bit depths right now are 24 bits. 16-bit is a CD quality still. Okay. So there you go. Bit depth sampling theorem. That'll wrap up some just a real foundational look at digital audio.